This is lecture 7 of the NITheCS SATACS category theory course in 2023. Today we're going to come back to generalized elements, and we will use them to introduce the notion of a functor between categories. So let's C be a category, and let us fix an object in C. We can call it C again, but we write it in a slightly different way, as you see on the board. So it's an object in the category C. I see that we have a message from Michaela that she's joining soon. And I also use this opportunity to silence my phone so we don't have a distraction during the lecture. Okay, so we've got a category C, an object C in the category. In the back of our minds, we can think of C being the category of sets, and the object C being a singleton. In this case, when we are here, so when this happens, Hom CX, for any object X in the category, Hom CX is bijective to X. So if I have a morphism F from, maybe I'll call this morphism small x instead, then that defines an element of X by evaluating the function X at the unique element of C. So that will be an element of X, right? And conversely, if I have an element of X, I can think of this element as a constant function that maps everything in C, but there's only one thing in C anyway, that maps that unique element in C to that element X. So it's a function that maps star to X. So Brandon, is it obvious to you that this will be a bijection? These two maps will give a bijection between the two sets.
Yes.
Maybe a graphical representation of the story is going to be convenient. So if I have, let's say this is my X and this is the C, we can see that we've got as many functions from C to X as we have elements in X, because a function is really determined by choosing a specific element in X, since there's only one element in C to evaluate the function at. Now, this suggests to us that if I'm back now in an abstract category, then maybe we can think of an object X in an abstract category as a set, because when we are in the category of sets, this X is really almost the same thing as this set, the set of morphisms from C to X. When C is an abstract category, X is no longer a set itself. It's just an abstract object in the category, but this thing is still a set in the abstract case. So seems like in the case of an abstract category, so back to C being an abstract category, it seems like we can do the following. So let me draw category C as an area like this, and let this be the category of sets on the right-hand side. So for every object X in the category C, we seem to have a corresponding set on CX. Remember, C is a fixed object. This C here is a fixed object in the category C. So if I have another object Y, I will also have the set from CY. And this way, I'm kind of turning the objects of the abstract category C into sets. So just a quick recap of what we did so far with for Michaela. We looked at the category of sets and the singleton, and we reminded ourselves the idea of a generalized element. So these are the elements of this home set, home CX. And when indeed we have C as a singleton in the category of sets, there is a bijection between home CX and X, given by these assignments. So if I've got a morphism from C to X, since C only has one element, the morphism determines an element in X. So that's how a morphism can determine an element. And the other way around, if I have an element, then it determines a morphism which maps that star to that element. Are you comfortable with the fact that this is a bijection, Michaela?
Yes, I am.
Fantastic. So now we move to an abstract category where we try to kind of keep this intuition that it seems like we can think of an object in a category, object X, as some sort of set once the object C is fixed for all the X's. So then for one X, we get home CX, for another Y, we get home CY. We're kind of turning objects of this abstract category into sets, which is quite fascinating, because these were meant to be some abstract structures, and now they've become very concrete sets. We can do actually better than that. We can even turn the arrows between the objects into functions between these sets. I'm now giving myself more space because I'm going to add another arrow as well. F and G. And let's see how we can, how these things give rise to functions between the home sets.
So is C like some fixed object in C category? Or
yes.
Oh, okay.
C is a fixed object. And we do this for one fixed C. And later on, we will change C as well. But first, we will learn how to do these things for a fixed C. So how can we turn a morphism F from X to Y into a function from home CX to home CY? If I pick an element of the home CX set, that will be an arrow from C to X. I need to describe what should the corresponding arrow be from C to Y. Any ideas? So this description should depend on the choice of a morphism F from X to Y.
Use f of x.
But f of x doesn't make sense. F is a morphism. If you meant by f of x, if you meant this, then I don't know what this is, because C is x is a morphism from C to x, and f is a morphism from x to y. We're now in an abstract category. Maybe it will become more obvious what to do once we draw these things. So once we draw these things together. So we need to produce an arrow from C to Y, and we have two things. One is an arrow from C to X, small x, and the other is arrow F from X to Y. Does this give us a suggestion how to get an arrow from C to Y?
Just a composition?
That's right.
That's what I meant.
Okay, well, I knew that, but well, I didn't know that, but I wanted to make it clear that. But we actually will think of that thing as f of x, right? Because now we are thinking of small x as a kind of generalized element of x. But yeah, so the composite fx. So what we are exhibiting on this diagram is a way to think of each object in a category as a set, and a way to think of every morphism in the category as a function. But all of this depends on having fixed one object of the category C, which in our case is the object C. We want this way of thinking about morphisms as functions to be compatible with the notion of composition. We actually want so okay, let me make it a bit more clear what I want to say. First of all, let's introduce a notation for this. So this is going to be written as hom CF. Okay. Back in the concrete case, if I go back here, what is hom CF? Let me move things around so I can fit the drawing. So we have this function that, let's say, maps this element to that one. So that's our small x. And we can think of this as an actual element of x when we are in the category of sets. And then we have a morphism from x to y. So that's a function f that will map this element to somewhere. Let's say here, let's call this thing small y, wherever it maps to. And now we're saying that we need to compose x and f, right? So we're thinking of this. So when we switch from the element way of talking about x to the morphism way of talking about x, then we are able to compose the function x with the function f. And of course, as you see from this diagram, which will give us a function that will be the composite, and that function will exactly select the element y. So introducing a bit of adjustment to my previous notation, if I, well, rather enrichment than adjustment. So if I write this element in the morphism way by putting a star as a subscript. So when I put a star next to an element of x, I'm thinking of it as a morphism from C to x. Then the formula becomes that f composed with x star equals sorry, that's a wrong way to write this. Formula becomes that f evaluated at x and then star. So thinking of f of x as an error from C to Y is the same as composing f with thinking of x as a morphism. So when I switch to morphism way of talking about x, and then I compose with f, the effect of that is the same as evaluating f at the element x, and then regarding that as a morphism. So there's a nice compatibility of evaluation of the function and composition. And because of that, we will have a further formula. Because of this formula, we will have another one, which is the following. So let me actually make some space to fit that other formula as well. What I'm doing now will be a little bit confusing because I'm like saying very, very, very trivial things with some a bit less trivial notation. When you say easy things with some not completely obvious notation, it may look complicated, but it isn't. So what happens if now I have another function g from y to z, function g from y to z? Then if I take g composed with f and evaluate that at x, this seen as a morphism will equal to g composed with f composed with x seen as a morphism. And why is that so? Well, we can derive that fact from this algebraically. Also geometrically, it's quite obvious to see that, but algebraically, we can also derive that. So g composed with f evaluated at x is, of course, the same as g evaluated at f of x. And then we apply this formula here in the case of f being g. I'm going to do that replacement in the case of f being g and x being f of x. Just doing a substitution. Then I get that this is equal to g composed with f of x seen as a morphism. And then I apply the formula again. This time I apply it for the original formula with the f there. This formula inside inside here. I will, of course, give me these brackets, but then because of associativity of composition, I can just write it without the brackets. So what this tells us is that composing g and f as functions is compatible to composing g and f as morphisms. In fact, maybe what I actually want to write is an even next step, where I group these like that, and then I say this is the same as g composed with f okay, I'm getting myself confused now. You see, even I also got confused. It's so confusing. So what do I want to say? I want to write down a formula that exhibits the fact that if I first compose f and g as functions, then evaluate it at x, and then think of it as a morphism, that's the same thing as taking the composite GF, no, I'm lost. Maybe you can help me. Maybe someone can help me. Is this the formula I wanted to write? So I want to have a formula that tells me that composing f and g as functions is kind of compatible with the switch to seeing elements as morphisms. Maybe I should draw a diagram, then it will help me. Okay, so we have here CX, and we have X, and we have this bijection between them. We have F, we have G, but we also have CY. So this is this function CF, the one that composes things with F, and this is the function CG. And I think, and this is each layer we have these bijections, and I think what I wanted to write, the formula I was looking for, is simply commutativity of the diagram we obtained here. So let me reposition this. So we have G composed with F here, and here we could draw. No, it's actually not the commutativity; it's something slightly different. We could draw here CG composed with F, right? Now, because this diagram commutes, this one here, let's call this small square one. What does it mean that it's one commutes? One commutes means exactly that. So we had this formula, remember? We had this formula. Now, this formula is written in terms of the reverse function, not the one that goes from x to x, but backwards. The star function is the one that turns elements into morphisms. So let me also make the adjustment here. I've got this function going the other way around. And now we're saying that if I pick an element x here, I consider the corresponding x star, and then I compose it with f. Remember, CF function, it composes things with f. So that's this right-hand side. That should be the same as first evaluating f at the element, and then looking at its star, which is the left-hand side. So in other words, commutativity of number one is exactly the formula that we have written here. Is everybody happy with this statement that formula one expresses commutativity of this top square? Great, I've got a confirmation from Alexandra. What about others? If you're not sure what I'm saying, then I'll be happy to re-explain. It's important to understand each step here because you see the whole thing is very confusing. So we better understand it step by step. Yeah, Michaela?
Would you mind quickly just explain it again, please?
Yeah, so what I want to establish now, well, first of all, do you agree with this formula?
Yes, yes.
Okay, I want to now establish that this formula, in fact, expresses that this diagram here commutes, which means that if I pick an element x going mapping it there and then mapping it down here gives me the same result as mapping it down there and then mapping it there. That's what I want to establish, that the sameness of these two mappings is the same as this equality. So I pick an element x, I map it there. It's going to go to x star. Then when I map it down here, it will be f composed with x star. Do you agree with that?
Yes.
On the other hand, if I map it down here, if I map x down here, I'm going to get f of x. And then when I map it there, this will be f of x star. Do you agree with that?
Yes, yes, yes.
So now these being the same is exactly equality 1.
Yes. Okay. Yes. Thank you.
Great, thank you. So in a similar way, the same equality 1 for now stated for g in the place of f will of course be commutativity of this square. You agree with that as well, right?
Yes.
Now, okay, so now we also so we can combine the two squares because 1 and 2 commute. We can say that the overall thing commutes. So this composite is equal to that composite, right? Because this composite breaks down into this, and the bottom part of that breaks down into that. So that's how we get the equality. Which then gives us that I've got a diagram with this arrow here being the composite of hom CG and hom CF. So the diagram with that arrow and the GF on the other side, that diagram commutes. So do we agree that this diagram commutes, the one that's marked with blue?
Yes.
Fantastic. Now, we have another candidate for something going from CX to CZ. It is this one, applying the hom C thing directly to the composite GF. But of course, by substituting in the place of F here, substituting GF, right? We get that this also commutes. It's the same thing as Y1 commutes, but now applied for GF. So now we have two diagrams commuting, the yellow one and the blue one, right? Brandon, are you happy with that?
Yes, I'm happy.
But here we have a bijection, and here also. So wouldn't this make these two arrows equal to each other? Because after composing with these bijections, they both give the same map on the other side. Imagine you've got two bijective sets. So there's a bijection there, and there's a bijection here, and there's a function there. And now you're transporting this function by a bijection. It will only give one answer on the other side, right? Now, more formally, I could do the following. I could do the reverse of this bijection on this side, and then obtain this arrow. Because of the commuting diagram we had, this arrow will actually be, you know what, let's write this down, because if you're doing this for the first time, then it's more convincing to see the algebraic computations behind what's going on here. So I'm going to write out algebraically what I mean. Let's give a name to this bijection. Let's call it because it's determined by x, maybe we call it x star, this bijection, and this one we can call z star. So what we've agreed on is that Hom CG composed with Hom CF, and that thing composed with X star equals the composite Z star with G composed with F. But we've also agreed that the same composite equals Hom C G composed with F composed with X star. Lian, are you in agreement to what I said?
I think so, sir.
Alexander, are you also fine?
Yes, same here.
So then we can compose both of these with the inverse of X star. Right? And when we do that, X and X star inverse, they cancel. And eventually we get that this equals that. And it's this equality that I was after. I wanted to motivate this equality because now we're going to establish this equality abstractly. So it turns out that if I think of these functions f and g as functions between the Hom sets, and then I compose them, the result is the same as first composing them and then thinking of that composite as a function between the Hom sets. So this equals Hom C GF. That's what we got. Michaela, are you fine?
Yes, I'm happy.
So this is a very important principle because we're kind of now saying that this transportation of viewing the set X as the Hom set CX is actually compatible with how we compose functions. That's what this equality tells us. And we want to now establish the same thing on the side. Here we established it thanks to the bijections that existed with the actual X, Y, and Z. We don't have the X, Y, and Z as sets abstractly anymore. So we cannot use the same method of proof. In fact, you will see that the method of proof here will be even easier than what we had before. So I've got my F on the left side. Now that F gives rise to functions between Hom sets, Hom CF. I've got the G that also gives rise to a similar function, Hom CG, which does what? It maps an arrow Y from C to Y. It maps that to the arrow G composed with Y, just like what the other one did. But I also have here, now I can compose the F and G, right? I'm going to have then G composed with F, and that will itself also give rise to a function between the Hom sets here, which will be just the Hom C of that composite, Hom C G composed with F. But on the right-hand side, I could have also individually composed these functions. And the question is whether that composite equals this or not. That's exactly the equality we had before, right? The question is whether Hom CF composed with Hom CG, whether that equals or not Hom C G composed with F. So let's investigate this question. We pick an element x of hom CX, so we can display it here. Then applying to that element this function is exactly composing x with f, so as we have right here. And if I apply to that further g, the hom CG function, it means composing fx further with g, right? So in the end, I get g composed with f composed with x, right? So let's write also the corresponding algebraic computation here. So I'm going to make this a bit smaller. So I take my hom, so I'm trying to evaluate this composite as an element, right? So I take my hom CG composed with hom CF, and I want to apply that to X. What does that equal to? Well, that's the same as applying this first to X and then applying that to X, which will be G composed with F composed with X. Now, what happens if I apply this right-hand side to X directly? Then it will be what? So what is hom CG composed with F applied to X? Isn't it G composed with F composed with X? Okay, so are these two things equal to each other?
I think they should be.
That's by associativity law of definition of a category.
Yeah.
In fact, we now get an interesting insight to the associativity law. Associativity law basically tells us, I mean, you can see it's easily that these two things are equivalent. Associativity law becomes now equivalent to this equality. So associativity law is designed precisely in such a way that seeing morphisms as functions between the hom sets, composition of morphisms is compatible with evaluation of the functions on elements. So I'm just going to reorder my equations. So I've got the chain of equalities here. Okay, so this equality now has been established abstractly as well. Michaela, are you okay with that?
Yes, I am. Thanks.
Okay, so there is more to say here. Not just composition. I mean, the definition of a category has also another ingredient, right? This other ingredient is presence of identity morphisms. And let's see if identity morphisms of the category are now compatible with identity functions. What does that mean? That would mean that if I take, if I take X, an identity morphism of X, when I view X as a hom set, hom CX, that this hom C of identity will match exactly with the identity function of hom CX.
So are we like trying to construct some functor?
Yes. Yes, we haven't defined a functor yet in this course, so this will actually be used as a motivation for defining a functor.
Yeah, because it seemed a lot like it, because we like first tried to distinguish composition, and now I see identity.
Yes, you're absolutely right. So let's compute what does hom C identity does. If I pick an element X here, it will be mapped to identity X composed with X, right? But by the identity law of the category, this is actually equal to X. So, which is the same as identity function of hom CX applied to X. So we get the equality we claimed we would get, which is that C identity equals the identity of CX. Okay, so summarizing what we've established so far, we've got these two categories, the category C and the category of sets. Every object in C gives rise to a set. It's a way of thinking of X as a set. And this way of thinking of X as a set, it extends to morphisms as well. We can think of morphisms as functions. And this whole thing is compatible with the structure of the category, with composition and with the identity morphisms. If I now represent this functor that I said I would call it later, so such a thing is called a functor when you have a way to transport between categories that is compatible with composition and identity morphisms. So let's call this capital F. So what does capital F do in our case? Capital F of X is the set CX. Forgot to write here CF. And capital F of F is CF. Now those two equalities we had, this equality 1 and equality 2, which we have also established, can now be rewritten in the following way with the capital F notation. F of G composed with F equals F of G composed with F of F. It's exactly this first equality here, except that I've swapped the sides now. So here is my F of G, here is my F of F. Their composite is equal to F of GF. So that's the same as this with left-hand side and right-hand side swapped. And then also I have that for every identity morphism, this equals identity morphism of F of X. You see, F preserves the structure of the category. It preserves composition. It preserves identity morphisms. F is a morphism of categories. It's a homomorphism, rather, of categories. A homomorphism of categories is called a functor. Okay, so this clarifies a bit what we were talking about generalized elements before. So once I fixed an object in a category, I fix an object C in the category, then I can think of objects of my category as sets, and this process of thinking of an object as a set is actually a formal process. It's a functor, and it's given by assigning to objects sets and assigning to morphisms functions in such a way we say that this process is functorial, in such a way that composition is preserved and identity morphisms are preserved. So the language of generalized elements that we spoke of in another lecture can be now formalized as making use of the of functors like this. And in fact, this functor depends on the object C, so maybe we should put a subscript C in our case because of that dependence. Now let us look at the way we used generalized elements to explain the definition of a product of a category. And let's try to rephrase it as a certain property of the functor F. So what happens now if in our setup of transporting between these two categories, on the left side, we consider the product of X and Y with its product projections pi1 and pi2. What will be F of X? Well, F of X will be CX. This will be hom C x cross y, applying f to x cross y, and this will be hom cy. And what about the functions between them? So pi1 will be transported to hom c pi1, and pi2 will be transported to hom c pi2, right? And just keep in mind that this is what we call fc of x, and that's what we call fc of pi1. This is what we call fc of x plus y. This is fc of pi2, and this is fc of y. If I draw the c on the other side, right, we have this definition of a product, which tells me that every two things there determines uniquely that thing. In fact, we can write this as hom x cross y being bijective to hom cx cross y being bijective to hom cx cross hom cy. If you remember, this bijection was actually one of the ways we defined the product. The universal property, we did explain that the universal property that for every f and g that is a unique h is equivalent to having a bijection here. It's not an arbitrary bijection. It's the kind of bijection that in this direction, it assigns to h the pair pi1 composed with h and pi2 composed with h. Okay. Now let's draw that in on our diagram upstairs. So I have my own hom cx here multiplied with hom cy, which I know is the product of, okay, sorry, let me make a bit more space. The category of sets has its own product, right? And we know what the product in the category of sets is. It's Cartesian product of sets. So this object here is a product in the category of sets. And there are these product projection maps, which are exactly the two projections, right? So let me call them pi prime 1 and pi prime 2. What do? They take a pair fg and they map it to f with pi 1 and they map it to g with pi 2. Now the bijection we get here, this bijection, that maps h to this composite, actually tells me what? It tells me that if I take h, right, I map it there by the bijection, I must get an ordered pair whose first coordinate is exactly this function applied to h. Remember, this function applied to h is just pi 1 composed with h. So this bijection is such that this triangle commutes, triangle 1 commutes, because of the first coordinate here being pi 1 composed with h. And similarly, because of the second coordinate being pi 2 composed with h, it makes triangle 2 commute. Should I re-explain this?
I think it will be nice, actually.
Okay, yeah, I went a bit quick. I'm going to write it out all algebraically to make it more apparent what we're doing here. Okay, first of all, do we remember how the universal property of the product is equivalent to having this bijection for every c? Is that something we remember or we don't? Because if we don't remember that, we're going to explain that as well.
Yeah, I think I remember it.
Does everybody, I want everybody to remember it. Does everybody remember? Brandon, Michaela, and Leanne? It's okay if you don't remember. Huh?
Yes, I remember.
Fine with me as well.
I remember as well, sir.
Okay, fantastic. Let's give a name to that bijection. Let's call this bijection B. I'm going to call it beta. So let's compute the composite pi 2 prime composed with beta. And let's actually compute its value at some h. Okay, so it's going to be pi 2 prime of beta h, right? Just definition of compositional functions. What is beta h? Beta h is this thing. So it's pi 2 prime of pi 1 composed with h, pi 2 composed with h. Now, what is pi 2 prime? Pi 2 prime is a projection of the Cartesian product. It will take a pair of elements of the two sets and map it to the second component. So it's equal to pi 2 composed with h. But what is pi 2 composed with h? Pi 2 composed with h, I claim, is exactly C pi 2 applied to h. Let me remind you of that. This is how we define CF, right? CF of x is exactly f composed with x. So C pi 2 of h is exactly pi 2 composed with h. Is everybody okay with this chain of equalities?
I'm fine with it.
I'm happy.
Fantastic. But now I have an identical chain of equalities by talking about pi 1 prime instead of pi 2 prime. So let me write that as well on the other side here. So let me do the adjustment. Instead of 2, I will just write 1. It's exactly the same story, but we now do everything with index, with subscript 1. Everybody happy with that as well?
Yep.
Yes.
Okay. Now, what does the first set of equalities tell us, the final conclusion of that? If I look at the first term here and the last term, it tells me that diagram 2 commutes, doesn't it? Here's beta, here's pi 2 prime, right? So what does it mean for 2 to commute? It means that pi 2 prime composed with beta equals C pi 2. And that's exactly what we established because we evaluated these two functions on every element h, and they're equal. Similar way, diagram 1 commutes. As you see, it's equality of these two things we establish here, since h is arbitrary. So the bijection beta, which we have by definition of product, remember, definition of product is equivalent to saying, that's the thing I asked if you remembered or not. It's equivalent to saying that for every c, that is this specific function that's a bijection. So now we can rephrase it by saying that the definition of product is equivalent to saying that for every c, there is a bijection here making 1 and 2 commute. But doesn't that mean that for every c, f, the functor fc, maps this diagram into an actual product diagram? Remember, products are unique up to isomorphism, and anything isomorphic to product is still a product. So if I have a bijection here, in other words, an isomorphism in the category of sets that's compatible with the projections, because this is a product diagram, this will also be a product diagram, and it's actually equivalent to this being a product diagram. So we get this little theorem that a diagram like this is a product in the category C. If and only if for every object C in the category C, the corresponding diagram FC applied to X, FC applied to X cross Y, and FC applied to Y, with the projections being FC applied to pi 1 and FC applied to pi 2, this is a product in the category of sets. So something like this being a product in the category of sets is equivalent to the actual thing we know is a product in the category of sets, which is this one. So we're claiming basically that this thing is a product if and only if this is a product, right? Okay, we know that this is a product if and only if we've got this bijection, right? Making triangles commute. But we also know that this thing is a product in the category of sets. And we know that having another diagram that's via an isomorphism relates to this diagram with these commutative triangles is equivalent to that other diagram being a product diagram in the category of sets. So now in the end we get that this thing is a product if and only if for every C this thing is a product. Does that make sense, Alexandra?
Yep.
Michael, are you also okay with that?
Yeah, I'm happy, thanks.
So philosophically, it's a very important fact because now
So
we're
I
saying
didn't
that
quite understand it in another direction. So if we take like some object C, I get that it will be a product on the right side, but I don't understand the another direction. So if for every C, it's a product on the right side, it will be the same on the left side, or what?
so yes. So if for every C the right side is a product, so this being a product, because this thing is already a product, this being a product is equivalent to there being an isomorphism between those two products.
Okay.
So if this is a product for every C, it means that there is always this isomorphism here.
So by uniqueness of product here?
Yes, 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 yes.
Okay, all right.
And for there to be such isomorphism is exactly this equivalent way of stating the universal property. So that's how we get it backwards.
Yep, that's fine.
Yeah, but that was a good question. So philosophically, this means that we can now think of this theorem as actually the definition of a product. So remember, the whole point of this idea of generalized elements is that we want to think of, so it gives us a language in which we can think of individual objects of the category. We can think of them as sets. This is via the FC functors. Now, in the category of sets, we know very well what it means to have product. This is the usual Cartesian product, right? So if I want to generalize the notion of a product to an abstract category, if I had known about these functors FC, I could have said, why not define a product in an abstract category to be a diagram such that applying FC to it always gives me a product in the category of sets. If this language of generalized elements is powerful, then this should be a powerful notion of a product we get on the abstract side. And indeed, the notion of a product on the abstract side we see now is equivalent to that. So that could have been another way to approach and arrive to the same definition. And this will work not just for products, but all limits. So last lecture we talked about limits. So this thing we established in the theorem actually works for all limits. A similar theorem is true, but it doesn't work for colimits. More generally, for all limits. Okay. All right, so this is the part of the lecture today which touches on generalized elements. And maybe, Alexandra, do you feel that you understand better what generalized elements are now?
Yep, totally.
Fantastic. You asked me, so Alexandra wrote to me a message asking if there is any literature on generalized elements. And I don't think there is this topic included in any of the standard textbooks. It's usually, the language of generalized elements is usually something that's used in papers for shortcut proofs, just by reducing a categorical proof to a set theoretic one. But I haven't seen a book where this topic is explained, so I didn't even reply to Alexandra because of that, but I was having in mind that we would touch on this in the lecture. Okay, great. Now we abandon generalized elements for a bit, and we do something different that comes out from what we did here. This idea of transporting from one category to another, which we now see is quite useful, can work between any two categories. On the right-hand side, we don't need to have the category of sets. So I'm now talking about the idea of transportation that obeys these two laws. Such a thing is called a functor. And let's define it. And then also give some examples of it that are different from the ones we already considered. We will come back to the story of the Hom functors and generalized elements a bit later on via something called Yoneda embedding, which will be even better way of formalizing the language of generalized elements, but it builds on what we discussed today. But before we do Yoneda embedding, we need to not just define functors, but we also need to define natural transformations between functors. So we have some work to do before we can come back to generalized elements. A functor f from a category C to a category X is a pair f0, f1 of maps. So f0 goes from C0 to X0, and the zero notation is just another way of writing objects of C, and the collection of objects of C, and the collection of objects of X. And f1 is a map from C1, which is just another way of writing the collection of morphisms of C to X1, which is morphisms of X. So we have a mapping of objects, we have a mapping of morphisms. But these mappings should satisfy certain conditions. There is a nice diagrammatic way of writing these conditions now. Let's draw C0, C1, and we also draw C2. What is C2? C2 is the set of composable pairs of morphisms. It's a set of GFs such that the codomain of F, C of F is the notation for codomain of F for now, is equal to domain of G. And those of you who was here for or listened to the lecture on pullbacks and still remembers it, you will recognize that this is very similar to how pullbacks are constructed. In fact, this will be a pullback. We'll come back to this a bit later. So that's what C2 is. And why do we want to work with such an object? Because composition is actually a function that has domain such pairs, right? And two things are composable only when the domain of the first matches the codomain of the second. We cannot just compose any two morphisms of the category, right? We can only compose in certain situations, and the situations where we can compose is exactly those satisfying this equality. And then we have other maps. Here is the domain map. Here is the codomain map. And we also have a map here, the identity, choosing the identity arrow for each object. So composition map maps GF into the composite G composed with F. Domain map maps a morphism F to DF, which is the same as the domain of F. The codomain map maps it to codomain of F, which we write as C of F. And finally, if I've got an object X, by the I map, it's mapped to I of X, which is another way of writing identity of X.
Sorry, I kind of missed it. What are like C2, C1, and C0 here?
So C1 is what it was before, morphisms of C.
Yep.
C0 is objects of C.
Yes.
And C2 is the set.
Okay, all right.
So these are pairs of morphisms. So it's those pairs in C1 cross C1 that satisfy this equality. Okay, so we can draw a similar diagram for the category X. So we have here the corresponding domain map, the corresponding, let me write C as a subscript here. We have composition. This is composition for C, this is composition for X. Now, the reason why I took the effort of drawing these things out is to make the definition of a functor even more transparent than it is. So our F0 will be a map here. F1 will be a map here. And these two maps induce the map F2, which is defined this way. I simply map the pair GF to the pair F1 of G, F1 of F. But in order for me to be sure that this pair will be compatible just as this one was, I need to know that F is compatible with domain map and codomain map, and this is what I'm requiring by this diagram here. So all the arrows we see on the left side, the corresponding arrows with the right side will be compatible to them by the F maps, and that's the definition of a functor. So when I said here is a pair such that, now I'm going to write the conditions as equations, separate that from these pictures, which explain the notation in those equations. Such that, firstly, C X composed with F1 equals F0 composed with CC. Secondly, maybe I'll keep it together. This one together with, no, let's make it separate. D map composed with F1 equals F0 composed with a D map. So if I take a morphism, I map it by the functor, then the domain and the codomain of that mapped morphism, right, will be the same as mapping the domain and the codomain of my morphism I started with by the functor. Then the equality we had about preservation of identity laws, sorry, of identity morphisms, can be now written as F1 composed with IC being equal to IX composed with F0. And finally, the law we had for composition is the same as saying that F1 composed with the composition of C equals the composition of X composed with F2. So on the picture, this means the following. On a different picture, this is a zoomed out picture, the one we drew before. And if I look inside my categories now, a zoomed in version of the picture, what I'm saying is that firstly, if I've got a morphism, then f of f will be a morphism from f of x to f of y. This is 1 and 2. Then what I'm saying is that the identity of x will map to, so this is the mapping of the functor. My category is C and X here. Identity of x will map to identity of fx. And finally, compatibility with composition. So if I compose them and then map, the result is the same as first mapping them and then composing. Let me know if I should re-explain some features, some parts of the definition of a functor. So this should equal to f g composed with f of f. Everybody happy with the definition of a functor?
Yes.
Okay, fantastic. Leon, are you also good, or do you want me to re-explain something?
No, I'm fine, sir.
Okay, fantastic. Now, there is a reason why I showed you, I mean, I could have drawn the definition, I mean, stated the conditions just in terms of these diagrams we see here. There is a reason I showed you this one. And the reason is that this suggests us how to define a category inside another category. And this is now very confusing. But now think of this diagram. We could implement this diagram inside an arbitrary category. At the moment, it's a diagram of collections of objects and maps between them. They're not even sets, because in the sense, C1 could actually be a class in the sense of set theory. It doesn't have to be a set. But still, if I take the category of classes, where now the collection of objects is even larger than a class, I could maybe use this diagram to define what is the category inside a general category. But I need to learn how to build the C2 because the composition map must come from C2. And that can be done using pullback. So let me show you how to do that. So let's consider these two maps, the domain map and the codomain map. And let's define C2 as the pullback of this diagram. So we have the first projection of the pullback. I'm going to write this as pi1 now. Before I didn't, because I didn't want to confuse with the product projection. But since I don't care about products now, just pullbacks, I'm going to use pi1 for the pullback projection. In the category of sets, remember what this is? In the category of sets, this is the same will be true in the category of classes. This will be just the set of pairs of elements here and there, such that D of one element equals C of the other element. So this indeed generalizes what we want to generalize. Michael, are you okay with that?
Yes, I am, thanks.
Okay, so now the definition of an internal category in another category. So an internal category in a category, I'm going to call this A, is a diagram in A such that, and now we're going to discuss what the conditions on this diagram will be. But before discussing conditions, let's match it with our intuition, what's going on here. So for the time being, think of this A as being the category of classes of sets, so large sets. Then C0 is just stands for a collection of things we will call objects. C1 is the collection of morphisms. D is the domain map. C is the codomain map, and I is the choosing the identity map. C2 is defined by this pullback. So the fact that it's a pullback, we can mark it like this, or we could also say PB. Maybe it's more convenient to say PB. So C2 is also in the general definition I'm stating here. C2 is defined by the pullback. We actually had a notation, suggestive notation for a pullback. So according to that notation, this would be written as C cross C with subscript with a pair DC. And so this data that I'm giving here is exactly the data for a category. We've got objects, morphisms, and composition. And composition is indeed defined exactly for those F and G, where domain of G matches with the codomain of F. So domain of G matching with the codomain of F. So all we have to do now is to state the definition of a category is to write down the axioms for a category with the composition law and things like that. Well, first of all, before we move to the composition law, let's remind ourselves that the identity morphism of an object is such that its domain and codomain is that same object. In other words, decomposed with I must equal to identity of C0. C composed with I must equal to the identity of C0 as well. What does this tell me? It just tells me that if I've got an object X, then its identity arrow has domain and codomain the same X, right? If this is true for functions, the left and right hand side functions, then it means that their values at every X are the same, but the value of this at X and the value of that at X is exactly domain of identity of X, and this is the same X. So we get that this equality expresses that the domain of the identity arrow is the same X, and similarly this one expresses that the codomain is the same X as well. We now want the other laws. One is associativity of composition, and the other is the fact that when we compose with identity morphisms, we get the same morphism back. And to construct these laws, first we will have to do some kind of a game with pullbacks. So I'm going to draw a large diagram now. Here I've got my C1, here I've got D, here I've got C, and here I've got this pullback, C1, I'm going to write C2 here. So this is pullback, I1, I2. Now once I compose the two morphisms, right, when I do the composition here, I arrive to C1. Now what I want to say is that this composite, so before we even do the associativity law, I want to say that the domain of the composite, if you look at the composite, its domain matches with the domain of F, right? And the codomain of the composite matches with the codomain of G. That's an important piece of the definition of a category, so I want to be able to say that here as well. Okay, so I compose, right? I apply the composition map, and then I take the domain. And this must match with, no, sorry, I take, on this side, I want to take codomain. This must match with what? Let's see. Codomain of the composite matches with the codomain of G, right? Now, how do I extract G out of my pair? Remember, here we've got the pair GF. Pi1 will project it to the first component, and that's exactly the G. So I will have my G here if I map it this by Pi1. And then I further want to map that by C. And now I want to say that by transporting GF by composite here and then composing with C is the same as transporting these by the composite of these two maps. So in other words, this diagram with identity being at the bottom commutes. And similarly, maybe I'd rather, instead of drawing identity here, maybe I'd rather make it into a triangle. So there we go. So now this diagram commutes. And similarly for the other one, for the fact that the composite will have same domain as F. So to extract F out of the pair, I apply Pi2. I will get then F here. So Pi1 and Pi2 map these things to G and F respectively. And then I take the domain of F. So this composite will give me, out of the pair, it will give me exactly the domain of F. And I want that to be the same as the domain of the composite. So I also want this diagram to commute. So we can add these two equalities to the definition. So number 3 says that maybe I should actually not use circle here because it will confuse me with the composition of arrows in the A category. So let me call it something else. Let me call it M for multiplication. So I'm going to write my composition inside this internal category as M. And then I have M here as well. And so 3 says then that C composed with M, so that's this composite, equals C composed with Pi1. And then number 4 says that D composed with M equals D composed with Pi2. Okay. Now let's try to see if we can express, first maybe it will be easier to express the identity laws before we express associativity. So I want to turn the identity law into diagrammatic representation so I can express it abstractly inside any category A. By the way, before we move on, did I lose you or are you okay with what we're doing so far?
So I quite don't understand how you how does D work from C1 to 0?
So C1 is the collection of morphisms of the category.
Yep.
And C0 is the collection of objects.
Yeah, how like get an object from a morphism?
By taking the domain of the morphism.
That's what D and C stand. Okay. Oh,
Yes, yes. I said that. I said that right here.
Okay.
Any other questions? Brandon, are you okay with what I'm doing so far?
All good on my side.
Okay. Leanne, what about you?
No question, sir.
And Michaela?
I'm all good, thanks.
Okay. Okay, so I now want to write down diagrammatically the fact that so that I can express it as a condition on my internal category. The fact that if I have identity morphism of X and I compose that with F, so F composed with identity morphism equals F. I want to write this down. In order to write this down, I need to represent it as M of something, and indeed it's M of the pair identity X. So that must equal F, right? But now I want to be able to begin with F, and so that will be inside C1, right? And get something in C2 that will be representing this pair F identity. So I want an arrow from C1 to C2. And remember that C2 is a pullback, right? So by universal property of the pullback, specifying arrows into C2 will amount to specifying arrows into C1 as long as some diagram commutes. So let's write this down. So C2 being a pullback of D and C, in order for me to get an arrow to C2, I need an arrow into C1, two of them actually, in such a way that composing them with D and C, they're equal. So that then I can invoke the universal property of the pullback and say that, and there is a unique arrow here that makes this triangle and that triangle too. Well, I mean, it's easy to see what I want from this map and that map, right? I want to map F to the pair F identity. So it should map here to F. So F mapping here to F, that would make this which map? What morphism should I take here so that I ensure that F maps to F? So I want F here to map to F there. With the other one, I would want it to map to identity of X. So what do you think should this morphism be?
Identity, maybe?
Yes, it will be identity of C1. Now, what about the other one? From F, I need to create identity of X. So what is F? F itself is a morphism from X to Y. How can I create identity of X out of F? Well, maybe first I can create the domain of F, right? And then create out of that the identity of the domain. So this morphism will actually be a composite of two morphisms of the domain morphism from C1 to C0, and then of the I morphism. Okay, but now to generate this arrow from C1 to C2, I want to confirm that D composed with identity of C1 equals to C composed with I composed with D, right? Okay, so I want to confirm this. So let's compute the left-hand side. Well, maybe we compute the right-hand side first and then arrive to the left-hand side. So what is this composite? This is C. Originally, it was like this, right? But the bracket doesn't matter because composition is associative. So if I put brackets this way, I get C composed with I. What is C composed with I? C composed with I is identity. Remember, I will be selecting the identity morphism of an object, and then C will be taking its codomain, which is the same as the object itself. So this composite is identity. It's the identity of C0. That, of course, is D, and of course, D is the same as D composed with identity of C1. So this diagram here is indeed a cone over this one, and therefore, by definition of a pullback, we'll have such a unique morphism, which we are going to write as a pair. because it's determined by these two maps. So I'm going to write it with angular brackets to indicate it's going into pullback of this product. 1C1 and the composite ID. Okay, now when I further map that, so now I've been able to generate the process of mapping F to the pair F identity as an arrow from C1 to C2. If I further map that to M of this thing, this is something we can do. It's just composing with the M function, right? We want that to be equal to F. So I want what? I want M composed with this morphism to equal what? So if these were sets, I want this composite to take F to itself. So what should I write here? M composed with this equals to what?
Would it be the identity of C1?
Yes, it will be. Thank you. This is our axiom 5. Make sure it's visible better. So this is 5. Okay, so far we've got identity only on one side. I want the same thing to happen on the other side as well, and I hope you will believe me that that will be just a similar formula, except that now I'm going to put I composed with D on this side, and then that. Maybe I should make it a bit more explicit here, but it looks like ID is one word. I compose with D. I compose with D. Putting this on that side will give me but this time it will not be D, right? It will be codomain. Okay, I'm going to elaborate on that. This will be identity of C1 as well. So why is it codomain and not domain? So here we consider the case when we're composing F with the identity morphism of X, but the other identity law will be dealing with the identity morphism of Y, which is the codomain of F. So for the other law, I will need the codomain map rather than the domain. Okay, now final axiom. One more axiom remains. This will express that composition is associative. So for that, something we need a bit more complex. Associativity of composition states that H composed with G composed with F equals H composed with G composed with F. Okay, now I want to turn this into diagrammatic thing. So obviously I can see here I'm starting with 3 variables, H, G, and F. And I want to be able to create out of them by some functions that I need to define. Firstly, I want to create HGF on one side, and on the other side HGF, and then further I want to create HG composed with F and H composed with GF, and then I will say that these two must be equal. So we are beginning with triple HGF, but these are not arbitrary. This is not arbitrary triple. It's a triple such that the arrows match, right? So HGF. So you see, it's a triple HGF such that the domain of H is Z, and the codomain of G is Z, and the domain of G is Y, and the F has the same codomain as the domain of G. Kind of almost like a triple pullback. Huh? So let's consider this triple pullback. So I'm interested in 3 arrows. So these are the sets of arrows drawn 3 times because I'm going to be interested in 3 of them. And then I'm going to call this C3. What I want here is the thing that selects the kind of triples that are representing such diagrams. So I will have 3 projection maps here, pi1, pi2, and pi3. Because we already used pi1, pi2 for the other pullback, I'm going to call these things pi1 prime, pi2 prime, and pi3 prime. Now what I want is that when I select the first two, when I select H and G, I want the domain of H to equal the codomain of G, right? Domain of H, which is Z, equals codomain of G, which is Z. So selecting H out of the triple means applying the pi1 map. So I want, when I apply the pi1 map to the triple, so the triple is an element here. When I apply pi1 to it, I get H here, and I want the domain of that. So I can draw the domain, I can get the domain of that by applying the D map. But I want that to be the same as applying the codomain map to G. On the other hand, the domain of G should be the codomain of F. So I have another diagram here. And now I'm going to take this diagram, and I'm going to take its limit. And this limit C3 will model exactly the set of those pairs, or those triples, sorry, where H, G, and F match into the following picture. So this you will have to believe, because we haven't yet, unless you happen to have done the homework, we haven't yet computed all kinds of limits in the category of sets. So we don't have yet a precise understanding of this limit. But it turns out that when you work it out, it actually will be what we want. If you have a good intuition for pullbacks already, it will not be hard to believe that this should be so. Okay. What I want now is to compose the first two components, H and G. This will land me where? If I compose H and G, I will find myself exactly, so this will be pair H, G, and F, right? And that's exactly a composable pair. So it will actually land me in C2. So let's draw the pullback diagram for C2. So I'm looking for a map into the pullback. And as we know, maps into pullbacks are generated out of cones over this diagram. So I'm looking for a cone over that diagram in such a way that composing that with first projection, I want to get exactly this composite HG. So how do I get the composite HG? Well, first I need to extract the two coordinates, the H and G. Think of them as being inside a pullback. Indeed they are. I mean, look, this diagram here is exactly the diagram over which C2 is a pullback, right? And I already know that this thing commutes, because that's what it means to be a limit, that it has to be a cone over the diagram, so this must commute with that. I mean, remember, a cone would formally have also these intermediate arrows, just like with pullbacks, we could eliminate them. We have these arrows and then these additional projections, and then these must be equal to that, and so this must be equal also to that, so that makes these two equal to each other. So I could draw in the C2 here. And then get an induced morphism right here. In a similar way, something will be used later, I could draw C2 there. Again, because it's D and C pair. And then I will get induced morphism there. actually, I could have made my life a bit simpler and constructed this C3 as a pullback of these two morphisms. Let's actually do it that way so that we don't have to take a guess of what the pullback should have looked like. I'm going to do that that way. Sorry about that. But these two limits will turn out to be the same, even generally. So now these are not dashed arrows anymore. I'm going to actually take the pullback of those two things. So remember, we've got pi1 here and pi2 here. Similarly, pi1 and pi2. These are the pullbacks, usual pullbacks we already know about. C2. C2 is the pullback of the diagram. And then we could take the pullback of pi2 and pi1. So here we'll have pi1 prime and pi2 prime. Now, with this construction, we've modified slightly the representation of what we're doing. Because now, as in general with pullbacks, it will be a pair of something from there and something from there, having common, the second component of the thing here being the same as the first component of the thing there. So it will not be a triple HGF, it will rather be a pair of pairs, because in C2 we have pairs. So it will be a pair of pairs, HG and GF. So why will it be so? Because HG is what lives on this side of C2, and GF is what lives on that side. And now I want pi2 of that, which is G, to match with pi1 of the other one, which is also G. So that's why I put the same G on here and there, because of the fact that this C3 will be a pullback over this one. Okay. Now I'm looking for a mapping that maps this quadruple into this pair, where, as you see in the first coordinate, we're evaluating by the composition map. And in the second coordinate, we just want to take the second projection of the GF. The two coordinates of C3 are given by C2 here and there, and the two coordinates of where we want to end up with are given by C1 and C1. So maybe we could build that map just by first by looking at the corresponding maps on the coordinates. I'm going to use green color for that. So I'm going to consider a map there and a map there. So this first green map is the M map, the composition map. The second green map is just keeping the F, right? So it's pi2. In order for me to get this dashed arrow, now I want this composite to equal that composite. That will then generate for me the dashed arrow, right? So let's see if that's so. D composed with M composed with pi1 prime. Let's compute what it is. If we look at our fourth axiom, D composed with M is the same as D composed with pi2. So I could write this as D composed with pi2 composed with pi1 prime. Now, pi2 composed with pi1 prime, it's this composite, right? And by the pullback property is the same as that one. So this is decomposed with pi1 composed with pi2 prime. But what about decomposed with pi1? Decomposed with pi1 is the same as C composed with pi2. So it's C composed with pi2 composed with pi2 prime. And that's exactly what we wanted, isn't it? So remember, we wanted this composite, which is decomposed with M composed with pi1 prime, to equal to this composite, which is C composed with pi2 2 composed with pi2 prime. So yeah, C, pi2, C, pi2, pi2 prime. That's exactly what we've got here. So once we know those things are equal, that guarantees this map here, and we will write this map again with angular brackets because it's something going to pull back, and that map is now induced by the two composites M pi1 prime, so this is the composite, and the other one, pi2 prime. Pi2 composed with pi2 prime. So what this map does, if in the case of the category of sets, it would map this quadruple to this triple. And now I want to further map it to their composite, which is just composing this with the M map, isn't it? So I've managed to trace these mapping as an actual arrow from C1 to C3 to C1. And this arrow is, I just want to fit in the axiom here. So as you see, this arrow is M composed with this thing. So I'm just going to copy paste what we've got here and insert it in my axiom. So we've got M composed with that thing. And that I want to be equal to a scenario where we do something similar, but we swap things around. We keep the H and we first compose G and F. And just like the other time, we're going to skip that. So it will be basically swapping these things around in this pair. So if this one was M composed with pi1 prime and pi2 composed with pi2 prime, the other one would be M composed with. So I need to now select the H, right? How did we select the F? We selected the F by taking pi2 prime and then taking another pi2 of that. How can we select H? We can select H by taking pi1 prime and then taking pi1 of that. So instead of pi2 prime, we will have here pi1 composed with pi1 prime. And the other one will be taking GF and then composing them. So it will be M composed with pi2 prime. Before it was M composed with pi1 prime. So that will be the other thing that I want that thing to equal to. So that's it. We're done with the definition of an internal category, where this axiom 7 represents associativity axiom. Axioms 5 and 6 represent identity laws. Axioms 3 and 4 tell me what the domain and codomain of a composite is. And axioms 1 and 2 tell me that the identity morphisms have the same domain and the codomain as the object itself is. Now, what is interesting about what we did here? Well, there are a few things that are interesting. First of all, I mean, I completely expect, and I would be quite surprised if this is not so, that not everything was clear in what we did here. And that's because we did it a bit rushed. But do you think that we did enough so that when you go back onto it yourself, you will be able to recover the details?
Yes, I think I definitely need to go back over it, but I think I'll manage.
Huh? So what do others think? Was it is it unrecoverable or is it recoverable?
Yeah, I think so.
Recoverable.
Yep.
Mm-hmm.
So to define like internal category, we have to have like fullbacks, yeah?
not
Yes.
results.
Yes. And this was kind of the first encounter with actually working with pullbacks, and that's what made it very confusing, because we didn't practice enough working with pullbacks, and now suddenly we made use of them. And yes, indeed, now the conclusion is that if I have any category inside that has pullbacks, inside it I can define an internal category. And if I had been working with this A being the category of classes of sets, then an internal category in that would be the usual categories we've been talking about thus far. And you might be surprised. You might think, how is it possible that we have this notion of a category that is such that we are able to define a category inside a category? That feels a bit confusing. But those of you who've seen foundations of mathematics using set theory shouldn't be too confused about that, because how does one develop set theory? One says a framework for set theory is a collection U of objects called sets and the binary relation epsilon, the element relationship, right? But then sometimes you want to define a universe of sets inside set theory as well. And how do you do that? You say it's a set V equipped with a binary relation R, in the sense of this set theory, a set V equipped with a binary relation R. But the axioms you will put on this will be just internal, set theoretically internal versions of the axioms you had here. So we have categories internal to other categories, just like we have universes of sets internal to other universes. So this feature of mathematical structure that allows you to define a structure of a similar type, but internally inside a structure of that type, is kind of suggestive of the fact that this structure can be used as a foundation for mathematics, which indeed is the case. So as you know, universes of sets can be used as a foundation for mathematics. That's the foundation that we use for our formal treatment of topics. Everything we've been talking about thus far is founded on the language of universes of sets. But it turns out that categories can also be used as a foundation for mathematics. You just need to put a few more axioms on a category, more than just having pullbacks. You need more than just that. And once you put sufficiently many axioms on a category, I mean, just like you need axioms on a universe of sets in order for things to work nicely. These are the Zermelo axioms, but also those introduced by Frankel and others. And once you put enough conditions on your category, then you can do mathematics inside it. And one of the things you can do is study categories inside there, just like you could study universes inside your Zermelo-Frankel set theory. But to study categories, all you need is pullbacks. You don't need advanced axioms, which makes it very easy, of course, but also it makes it possible to study categories inside other categories that are not good enough for foundation of all of mathematics. You can still do category theory in general categories, even if you don't do all of mathematics in it. And here is a very interesting question, which my father gave it to me when I was in the second year of my undergraduate studies. Ended up being my project. In Georgia, when I studied at the Tbilisi State University, it's the main university in Georgia, well, at least in the capital of Georgia, every year we had projects we could present at a conference, and there was even a competition got first, second, third place, and so on. So in my second year, I presented this project where I computed what is the I'm going to explain what I mean by compute here. Compute the category of internal categories in the category of abelian groups. In other words, we want to know what this equals to. Okay, so let me first explain what I'm talking about here. This is just the usual category of abelian groups. Objects are abelian groups and morphisms are group homomorphisms. To do this, first I need to define what are internal categories in the category of abelian groups. That's just applying this general definition to the category of abelian groups. So A will now be the category of abelian groups, okay? But we actually want to turn this into a category of its own. We want morphisms between internal categories, but these will, of course, be internal functors. Define morphisms as internal functors. And if you look at our definition of a functor, it was already stated in the language that it's easily adaptable to an internal functor. So you just need to express these things, and we already did that, right? You see, all our definition of a functor was already stated in the language that I could just copy paste that and get a definition of an internal functor between internal categories. So what happens here is that this thing simplifies considerably. But of course, it simplifies considerably up to isomorphism, not literally. So that the idea is to see how it simplifies. So when you take this data of objects and arrows to be abelian groups, this entire complex data of several arrows and several objects will simplify to very, very little information. Just because you're working with abelian groups and abelian group homomorphism, that simplification will happen. It's quite extraordinary, actually, how it simplifies. And basically, this question asks to find the simplification. Now, this homework is very different from all the other homeworks. This homework, if you work on it like full day intensively, it will probably take you at least a week to complete. So if you don't do anything else, if you just focus on this work, working from 9 in the morning till 9 in the evening, full day for 7 days, that's how long you will need to fully solve this homework. And then if you don't work for a full day, then you can calculate how many days you will need. It probably might take you 1 or 2 months to solve it if you're working on it every now and then. So it's not really a homework that I suggest you to do because you've got many other things to do. But in case you're like very, very interested in what we did today, and you want to solve a challenging mathematical problem based on what we did today, then this is the homework to try. Okay, I just want to summarize very briefly now what we did today because we touched on a few topics, and then we can end there. So we started this lecture with formalizing the language of generalized elements as functors that take us from the category C to a category of sets. We used how these functors are useful in defining concepts in the category C, such as products, but the same approach also applies to arbitrary limits. And then we gave a definition for a general functor between any two categories, not necessarily C and sets, but any two categories C and X. And in doing so, we came up with a way of writing down what a category is diagrammatically, purely diagrammatically. And this kind of suggests that maybe we could define such a diagrammatic category inside any given category, not just the category of classes. And then we attempted to do that here by defining an internal category. One of the main purposes of doing this was to show you the relevance of pullbacks. This is something we did in a different lecture. And so this was a good way to practice working with and also applying pullbacks. And then we came to this homework that's not pretty suggested unless you do have a lot of time to work on it. That's all for today. Any questions before we say goodbye?
So what is the main reason and motivation behind internal categories?
Several. So one is that if you want to do all of mathematics inside a given category, but that would require your category to have some additional properties. The correct term there is a topos. A topos is a category having necessary properties that would allow you to implement all of mathematics internally inside that topos. Then you also want to be able to do category theory such framework, and then that's how you would end up using internal categories. The reason why you want to do mathematics inside a topos is that we are working so far in mathematics, we're working in the topos of sets, but real world might not be a very accurate reflection of what actually goes on in real world. Topos of sets is just one topos, and there are many other toposes, and for various things can be modeled by other toposes other than the category of sets. So it becomes useful to know how to transport your mathematics to these other environments. Now, the motivation for considering internal categories in other categories that are not toposes, so where you can't do all of mathematics, but you still want to do internal categories, is that some concepts in the literature turn out to be equivalent to internal categories in a given category. And then you can apply your knowledge of category theory, internalize the version of it, to understand those concepts better. One of the examples is the concept of a cross module that comes up in topology and algebra that's related to topology. So a cross module turns out to be an internal category in the category of groups. Now this homework is about abelian groups. If we replace abelian with just groups, then an internal category there is equivalent to something that's called a cross module. And funny enough, it's also equivalent to an internal group in the category of categories. So this internalization kind of commutes in this case. Cross modules are complex mathematical structures that people are interested in. And knowing that they're internal categories allows you to, as I said before, derive some of its properties from the general properties of categories. There are also other cases when internal categories are interesting. In fact, internal groups themselves are special kinds of internal categories. And if you take the category of internal groups in the category of topological spaces, you get what are called topological groups, and they're also very important. A vector space is a topological group because it has topology also, right? A vector space over reals has a topology. This makes the underlying abelian group of the vector space a topological group because the vector space operations are continuous. So there are basically the short answer to your question is that there are various mathematical structures that turn out to be internal categories in suitable categories. And it's good that we can capture them and hence unify some of their properties just by studying categories in general. Are you happy with the answer?
Yes, it was kind of useful. Thank you.
Any other questions? Okay, great. Then that's it for today, and we continue next Saturday. Bye.
Bye. Goodbye.
Awesome. Thanks. Bye.